Okay, so if you agree, we can start with the second part of this day one of this seminar.
Okay.
So the second part of this seminar is focused on hydroelectric power. In our studies, as I already mentioned, we started with the power system and with wind turbines, and then during our investigations we compare normally the solutions that were developed for wind turbines when applied to hydroelectric systems. So it's why I'm just mentioning this application that was developed also together with our colleagues from the mechanical department of our university, through also a couple of or more than, let's say, 3 or 4 projects funded by the university and the region. We also were able to develop a hydroelectric simulator, which was including some pipes, valves, and electric generators in order to understand how the level of the energy that can be generated using, for example, what is called residual energy in the pipes or in the water distribution networks. It's the same application of the vertical axis wind turbines. So you can think of smaller applications, smaller installations, just for producing a reduced amount of energy that can be used locally, so is not injected into the grid, and just for example, for lamps in a street, in a smaller area, and is something that can reduce the impact of the use of the energy. So it's something quite important. So as we saw for the wind turbine, we start with some general considerations, a brief introduction, some general structure, and then some hydroelectric modeling issues, and then some concluding remarks. So hydroelectric power is called normally hydropower, is considered another renewable energy source. Of course, it cannot be depleted, so it's continued to use in the production of the energy. And it's very simply, so the energy of the falling water is converted, so from the mechanical point of view, into another mechanical source. So the hydropower is continually regenerated. So starting from this picture, so scheme, so the ocean is evaporating to the clouds. You have the rain. So in the snow, you have the runoff from the rivers, and then to the ocean, and then the evaporation. So it seems like a closed loop. So we are exploiting, as is written here. So you have a continuous cycle, is very important, like for the wind. But so because of the force of the gravity is written here, is shown here. So you have the water that is running out to the valley, and then you can exploit this energy of the water in order to extract some energy. So the idea is the same of this of course is a moving object in the park. So you are exploiting the kinetic energy, which is available from this object, which is going down to this hill. So as for of wind turbines, so also we have the same counter example, which was represented by water wheels. So the water wheels, they were exploiting the weight of the water for rotating this wheel. So is what they are called water wheels. So it's a revolving wheel fitted with blades. They are called blades or vanes. Vanes are the same word that is used in hydroelectric turbines. Vanes is this kind of place where the water can enter and transform its energy into a mechanical energy. So in principle, water wheels convert the kinetic energy of the falling water to mechanical energy. It's quite important. So the idea is represented in this picture. So the mechanical energy is a form of kinetic energy, like a machine. So the mechanical energy, of course, is the capability of doing a work. So any object that is able, in principle, like the picture here, that has mechanical energy is able to do a work. So this is the early development of also the use of a water wheel. So you have you can recognize, like as the image or the principle of the wind system. So you have here your renewable energy that is exploiting his mechanical power. You have a gearbox here because is transforming the lower speed into a higher speed. So with and in principle here it's used to grind grains and or, for example, as sawmills and as blacksmith equipment. So it was one of the earlier applications of water wheels. Of course, in more recent years, the water wheel technology advanced, and now we have this kind of turbines. So we have an optimization of the exploitation of the energy, because we have you see also the shape of the wheel, of the water wheel, was modified in order to capture the water entering in the system, and you see here a detail of the turbine. So you have these vanes that can be fixed, or also, or as the pitch of the wind turbine can modify the shape, the angle, in order to optimize or to control also the rotation or of the water, and so in order to so maximize the power extraction from this kind of turbines. So they are called water hydraulic turbines. And for example, in one of the early installations, again, it's almost the same years when wind turbine was developed. You can see here that again in United States they used this kind of system in order to capture the energy, and of course the produced energy by the time was really small, so 12.5 kilowatt, and it was used locally for lighting and giving the power, supplying the power to power mills. So it was a small, it was limited to a small area. So the principle of the energy is quite close, of the wind energy, of the hydropower, is quite similar to the wind technology. So you have a reservoir of water with a head. It depends on the power of the water. So you have the penstock, like this pipe, which encloses the capture the water and forces it to a hydraulic turbine with a generator. So the principle is very close. So you have a dam. The dam is installed for increasing the head. Then with this head, you are able to introduce the power in your energy, and then with this penstock you force the water to go through the hydraulic turbine, and then the water goes to the lower reservoir. And then the generator can be used for to be transmitted as the same technology of the wind turbine. So here we have an example of the generator. So you have the water which is forced into the turbine, and then the shaft. Well, in this case, you have the same shaft of the hydraulic turbine is connected to the generator, to the electric generator, which is used for generating power. So is the power, the flowing power of the water is directed to a turbine. And as the same principle of the wind turbine, so the turbine converts the water's kinetic energy into the mechanical energy. So we have another example which is the same. So there is a single generator. This is a simple generator with the transmission lines, turbine, the dam head, the higher reservoir, lower reservoir, and then the transmission system. So the idea, in order to, with the same consideration of the wind turbine. So if you remember, the wind energy depends on the radius, for example, of the wind of the blades and on the wind speed. So for the case of the hydropower, the amount of the energy depends on two factors, as for the same considerations of the wind that we made for the wind. So the flow rate depends on the radius, the size of your penstock. So flow rate is the quantity of the water flowing in a given time, and the head is the height from which the water falls. So they represent two factors that affect the energy, generated energy. So the greater is the flow and the head, the more energy is produced. So it's the same, almost the same factors that rule the wind energy. Of course, as you can see here, the flow rate, there are two pictures. The flow rate is the quantity of the water flow. So, of course, the more water flows through a turbine, the more energy can be produced. Of course, the flow rate depends on the size of the river, like here. The upper picture is higher than the size of the lower. So the flow rate depends on the size of the river and then the amount of the water flowing in it. So the power production is can be considered directly proportional to the river flow. This is one factor which rules the produced energy. The head, so here is an example of low head and high head. So the height from which the water falls. Of course, the farther the water falls, the more power it has. So it's quite simple. So the higher the dam, the farther the water falls, producing more hydroelectric power. So we can consider that the produced power is proportional to the head. So it means that this a proportional link, if the water falling twice as far, will produce twice as much energy. So is the effect. So normally, when you need to install a hydroelectric plant, you need to investigate the best position, the best place for installing. So it's important to determine from the hydrologist, determine the height and the amount of the pressure, because from the height it determines the quantity of the water flowing through the dam and then the generated power. So the water behind here the dam determine the pressure on the falling water, and then also the power generated by the system. So the power directly depends on the head, which is indicated here. So is the first effect. So the energy production, we can derive this very simple equation from our considerations. So the power is directly proportional to the head. So the head is so the power is normally measured in kilowatts, the head in meters, the flow is the amount of the water falling, which is measured in meters per second, and the efficiency. Of course, the efficiency depend on the, of course, the technology of the turbine, and, for example, on the generator and the quantity of the power which is converted by the generator. And the efficiency can range from, let's say, from the 60% from, for example, the first installed hydro plants to the 90% or perhaps higher for newer plants. So it's an important factor also for determining the power, the generated power. So normally there are different kind of installations. We called, as you remember, for the families of wind turbines that we considered at the beginning of this talk, like we mentioned, for example, the vertical axis or horizontal axis, or offshore, onshore. So also for the hydropower, we have different cases. For example, we call high head. So high head means that the head of the dam is very high. So normally, tall dams are sometimes referred as high head hydropower system. Of course, on the other side, it means that they introduce the higher impact on your environment. So you need to balance the head. The head of your installation is an important point, and the impact on your environment. And low head, you can see here that is a smaller installation. So when you are exploiting, for example, it can represent a situation of a river near to I don't know, very close to a city, to a town, to a village. And so in order to reduce the impact, you can exploit, for example, the head here. The head can be, for example, of no more than 2 or 3 meters, so it's very low. And so it represents the case of smaller hydropower systems that are defined as low head, because the height is very low. As I already mentioned, so low head hydropower systems are generally less than 6 meters. So the order of a few meters height is the definition of high or low head. As already remarked, we need to perform some environmental considerations, because high head hydropower systems can produce a tremendous amount of power. Unfortunately, large hydropower facilities, of course, they are essential for pollution-free generation of energy, but they have, as is highlighted here, undesirable effect on the environment. Of course, the impact is very high. It represents the side effect of these installations. However, if you want to produce more energy, you need to install high head dams. This is a picture of, for example, of the reduction in 2 years that the installation of large hydropower projects can be controversial because of the negative environmental impact. Of course, as you can imagine, also on the situation of in the real cases, of course, the installation of dams can produce, for example, flooding, the decrease of the fish population, the decrease of the power quality and the flow, and also the reduced quality of upstream and downstream environments. So you can see here an image of the installation of a dam, and the level of, for example, of this part of the, can be a lake, is increasing in 2 years. So you can understand very clearly that the impact can be very important. So it's why normally, as also in our investigations, we consider low head and low impact hydropower. So normally you can consider also the integration of these hydropower systems with some tools for helping, for example, fisheries to maintain and to survive in this modification. Because, for example, you can see here in this image I found on the web that in parallel with this kind of wheels is a very simple, is called an Archimedes turbine, which is very small. It requires a low head. As you can see, of course, also the energy production is quite low, like for the case of the vertical axis wind turbine. But on the same time, you can imagine of here you have, like, let's say, stairs for the, for example, for the fisheries that are able to go through, or to help them to go through this river. So it's something that can be built in parallel with your system. So it represents a way for using or installing systems that can have less impact on the environment. So one way, or one possible way, is to use low head hydropower. So remember, low head means less than 6 meters, like the case of these installations. And so they have also lower negative effects on the environment. And is the same of this installation. As you can see here, you have a low head here, but in parallel you have some a tool that is used by the fishes to go through the river. So it represents a reduction of the impact on this system. So in this case, you can maintain the river flow, the water quality, the watershed protection, fish passage, and the species protection, recreations and facilities, like here is represented in parallel, and also so you have a way for protect your, I don't know, the different species in your environment. So as for the wind, also the water is hydropower is a renewable energy, and of course, as we already mentioned, it is something very simple, but the future of the hydropower, of course, relies on this kind of renewable energies. And as we already mentioned, an integration, a proper integration on, for example, of the wind, hydropower, and is not mentioned here, but also with the photovoltaic systems. So solar panels can represent integration. So because you have discontinuities in your discontinuous energy resources, so you need to integrate them in order to have a continuous generation of your energy. It's very important, as we already remarked. So this is another example of low impact hydropower. Of course, we already mentioned it, the amount of the electricity depends on the water flowing. So in this case, the flow rate and the height of the waterfall they had. So in this case, as we already remarked, there are different kind of systems. And normally like in this case, the low head hydropower are generally less than 6 meters. And you can see again here in parallel, so you have the low head, and then a way that is used by the system in order to reduce the impact of your installation. So there are two kind of installations. One is called, two kinds of facilities. The first one is depicted here on the left. You have what we call the impoundment system or dam. So the dam is you have already seen that it depends on the height. You have the dam here represented by 1. 2, you have the penstock, the reservoir, the higher reservoir here, and then you have the hydraulic or the hydroelectric turbine, the generator 4 here, and then you have the distribution line, the transformation, for example, module or section, and then the distribution. Another way is called run of the river system. So you mean this second kind of installation, as you can see, you can notice from the picture, you have the main river here, so you don't really modify the river flow because you introduce you take some water from the main river, so you make like a deviation in your, so you have a second river that deviates from the first one, so also you can limit the impact on the main river, and then you use this water, so the diverted water, for using, for example, introducing a lower fall, and then to produce energy and then to transmit to the grid. Of course, the amount of the generated power different, but of course, as you can see here, the impact on the environment is totally different. So here on the left, you need to install a dam, which can be very high. Here you make a diversion in your main river, and then you deviate, for example, perhaps you can use a small area of your environment which is dedicated to your energy generation. So the impound, this another example of impound system. So you have which is partially hidden in the ground. So you have here the intake. You have, of course, you need to install some grids in order to filter the quality of the water, and you have the penstock as the previous, and then you see here that you have the hydraulic turbine with the generator, the distribution, the powerhouse, and behind or underneath your ground, you see here, and the river. So you can partially also play with or decide the impact. So in this case, you have the dam that holds the water. So you have a reservoir here. So the water is released through a penstock to drive the turbine, to feed the turbine. And then you can have, in this case, large and high-head hydropower to generate the power. And another example of, so this one in this slide can have a higher impact on your system. On the other hand, you can, as in the previous case here, you can a diversion, so you can introduce a smaller dam here. You can see here, so the impact is lower. You have a smaller canal here. You have like a smaller reservoir with a smaller dam, a penstock, and then your powerhouse, and then you restore the water to the main river. So this diversion, for example, introduces a lower impact on your system, and the difference with respect to the previous this application is that it requires a smaller, or in some cases, as in this case, dam. So the diversion is a portion that is just a smaller part of your stream. So also the impact on your system is lower. And because of this advantage, you have that very often is represented by a low head. As also here in this picture on the right side, you have again, for example, the snowpack or the rainfall, which are collected into a reservoir, and then you have the main river, and then a diverted, or can be a barrage, or a small river or a pipe, which drives the water down to the valley, and then you have the powerhouse here, and then you give the water back to the main river. So again, the impact is lower. As another consideration, considering the hydropower side, in order to give you some numbers, so there are, as for the case of wind turbines, also the dimension or the dimension of the power plants can produce different sizes of energies, different amounts of energy. So you can have the production, for example, of hundreds of megawatts of energy, and for example, like in this case, and supply the power of thousands of families. Or there are smaller, as you can see here on the picture on the right side, with this Archimedes turbine is smaller. Also the head is smaller, so it's called small or micro hydropower, because it depends on the amount of the energy. So the power plants are classified by how much energy they are able to produce. So in order to give you some numbers, so large hydropower, but they represent also the higher, they have also higher impact on your environment. They require a dam, and they can produce more than, so they 10 up 4 kilowatt. So the number is here 30,000 kilowatt. So this is the amount of the energy. From the other side, small hydropower, so you can see here, for example, the water is coming here from a diversion, and then is given back to the main river, and normally they can produce, so small, when you say small hydropower, it means that they can produce from 100, so lower load, and an amount of energy lower than, let's say, 3,000 kilowatts. And as we saw in the previous applications, hydropower facilities can involve small dam in the case, but also they can be represented by the diversion of the mainstream or run of the river system. We have also, in contrast to small hydropower, we have micro hydropower. So micro hydropower, perhaps they represent the case of the smallest installation. So micro hydropower have a capacity to produce less than 100 kilowatts. Micro hydro facilities normally are, as in this case you can see here, are installed typically as using the technology of run of the river system. So you have the main stream and then you have a diversion. This is a system, for example, is a picture that I found on the web in the Arizona Faults, is an example of low-head hydropower, and is a hydroelectric generation station, is an exciting example of low-impact renewable energy, because as you can see here, they maintain the almost a very low head, and is a public place where you can experience also some water. So you have you can see the waterfalls, and also you can contribute to the generation of the power. This is a very interesting example of is the simplest also system to produce the energy, because it doesn't require any control or any maintenance. Is the simplest way for producing energy. Of course, is also the way for producing the smallest amount of energy, because the technology is able to generate normally less than 100 kilowatt with this kind of turbine. So you can see here that the turbine is open. Also, the speed of this turbine is smaller. You can have the solution of, for example, installing in parallel more than one turbine, hydroelectric turbine or hydroelectric generation station, and so you can play also depending on the flow of the river. So you can adjust the amount of the quantity, the amount of the water, selecting how many hydroelectric stations are working in parallel. Is another way for installing different systems. So I want to conclude. So it's we can is this important feature that hydropower together, of course, again together with the wind power, is an important. It represents an important renewable energy source, which should be exploited, of course, in the best way. So it's why is also well, not really in the wind, in the hydropower, perhaps less than wind turbine, but it's why we are considering some solutions in order to improve the quantity of the amount of the generated energy, which depends on the control system. So it's why tomorrow we are focusing on a little bit more on the control solutions, and also on other ways for trying to reduce the cost of the energy, because as you can understand, the cost of the energy is one key point when you want to install your generation plant. So you need to take into account the cost of the energy, and of course, as we will see tomorrow, the cost of the energy depends mainly up to the 35% depends on the maintenance cost. So a way for limiting the cost of the energy is to reduce the maintenance cost. So we saw today that in the hydropower technology, the cost of the maintenance is lower than the one which is normally required in wind turbines, because wind turbines have some technologies that introduce also other elements that are mostly affected by faults. So it represents another difference between wind and hydroelectric power. Okay, we closed earlier, but I think we have space for questions if you want. So as I already mentioned,